Okay, so good morning, everyone, and thank you for having me here. And so, um, I am a team director of the RIKEN Trip Aegis and Polymer Omics team, and also I'm a vice director general of the Institute of Statistical Mathematics, and I'm a machine learning researcher. And today, uh, I can talk about the machine learning application in the field of material science and chemistry. Especially, I'd like to highlight great potential of integrating the data from the simulation and real-world application to realize the discovery of the new material. So let's begin by showing the basic workflow of the machine learning for material science and chemistry. And so now let's consider a black box system and input X and output. In context of the material science and chemistry, one of the typical input is a material, yeah, and output is a property. And collecting data on the input and output, and machine learning predictive model is constructed using the given data. And once such a model is given, we explore its inverse mapping in order to identify the new material exhibiting desired property. So this is a general concept applicable to a wide range of the research tasks in the material science and chemistry. So, but here, one of the critical issue in this research field is a lack of data. Okay? So compared to the other AI advanced research fields such as NLP and computer vision and biology, and data in our research field is much smaller than data in other research fields. So there are several reasons underlying the limited data resource in this research field. And one is come from the high cost of the data production, which involve uh, time-consuming and multi-step procedure of the real-world experimentation, as well as a computer simulation. And another reason comes from the high dimensionality of the material spaces. Yeah, so material spaces are generally quite huge and also hierarchical. So such a nature of the high dimensionality nature make it difficult to construct a common data because the researchers' interest, the highly biased in a specific local region in the entire material spaces. Okay. The another reason comes from the culture, and in general, researchers lack the incentive to disclose their laboratory data to open science community, and so this is a cultural issue. So it might be difficult to overcome such a issue within a short time period. And furthermore, an ultimate goal of material science is to discover the innovative material. But so in such innovative material exist the extrapolative region, no data are still available. Okay. So consequently, so most critical issue in this research field arise from the limitation of data resource. And the agenda of this talk is how do we overcome this big hurdle? Yeah. And so here is our vision. Yeah. So in a closed domain, yeah, so researcher in company or university lab, it might be difficult to acquire the massive data applicable for the training of the artificial intelligence model. Okay. So to overcome this challenge, and so what we need to do is to create the comprehensive and systematically designed open data platform. so with diverse domain. And so for example, the data from the computer experiments, such as first principle and molecular dynamics simulation and phase field simulation as well. On the other hand, the real-world data from the high-throughput experimentation or extracted from the literature survey also, of course, play a key role. Okay. So then, in the researcher in the closed domain, try to overcome the limited data by performing the integrative analysis in the limited laboratory data and also the massive amount of the data in the open domain. So this is our vision, and so we aim to realize. And so first milestone we need to address is we are aiming to address is to create the world largest computational database of the polymeric material. And so to achieve this goal, so we started around the 2020, and we begin the the project of developing the software called RadonPy. Okay, so RadonPy is a software developed to fully automate computer experiments for a wide variety of polymer materials, such as the all-atom classical molecular dynamics simulation or DFT calculation. Okay. So, as you know, the molecular dynamics simulation consists of the very intractable multi-step procedure. Okay. So the first, we specify the chemical structure of polymer repeating unit, and also additional calculation conditions are specified, such as polymerization degree and number of polymer chain and temperature, pressure, and so on. Then such a input is specified, and we perform the conformation search for the repeating unit based on the DFT calculation and the charge calculation and generation of a polymer chain and assignment of the force field parameter. And we create a simulation cell. Then we proceed with equilibrium and non-equilibrium energy simulation. And then finally, physical property calculated from the given MD trajectory. Yeah. So such a multi-step workflow is fully automated within RadonPy. And the latest version of our software, which has already been released through GitHub, implement the automated evaluation workflow for the 62 distinct property and structural and dynamic feature as illustrated here. And for the wide variety of the polymer system, and such as the homopolymer and copolymer and cross-linked polymer in amorphous state, and the uni-axis stretch orientation and crystallized state with a wide variety of the electric field, such as temperature gradient and applied AC electric field and so on. Okay. This is our software. And also, we are also with RadonPy, and we are now developing the world largest omics scale polymer database, which is called PolyOmics. Okay, and so this project has been supported by the FugakuNEXT program, and so massive computation resource has been allocated to our project. And in the last 5 years, so we have accumulated very big database of the polymer material from the automated computer experiments and using the RadonPy. And also, in order to accelerate the development of the RadonPy, and PolyOmics database, and we organize the academia industry consortium, which uh, including the more than 260 participants from the 3 national research institutes and 8 university and 36 or 7 company. Yeah. So here is an example of the uh, uh, data collection from the PolyOmics. And for example, this panel shows the joint distribution of 7 distinct physical property for more than 10 to 5 distinct polymer. Yeah, as you can see from this figure. So and so there is a trade-off between among the multiple physical properties. So it's formed Pareto frontier. So like this, and so with our database, so we can gain many insight. For example, where is a Pareto frontier we can achieve with the current material species, and what kind of the polymer species exists on the boundary like this. Okay. Okay, so here is a property list of the latest version of PolyOmics. So so this dataset has already been to be open, and also it should be noted. So our paper, and the preprint will be open maybe so today or tomorrow. Okay. So this is a list of the physical property in the latest version of the PolyOmics. And so, yeah, there are many property such as thermal property and mechanical property and electronic property and optical property. And in addition, and so we are providing the miscibility to commonly applied organic solvent and plasticizer. So this is a very important resource uh, to conduct the actual synthesis of the virtually generated polymer, which are registered in our database. Yeah. Maybe so. Number of data point is more than 5 million at this moment, and so which span the approximately more than 10 to 5 distinct polymer. Okay. So now let's see the result of systematic comparison of between the property calculated from the RadonPy and experimental observation. Okay. So as you can see from this figure, for the sum property, RadonPy calculated property exhibit a good agreement to experimental observation, but so the other some physical property, so there are significant inconsistency between the calculated and experimental property. Yeah. So one of the distinct feature of the RadonPy is okay. So RadonPy implement wide variety of the standardized workflow for the computation condition. So such a condition has been determined by expert based on the result of the systematic comparison with the experimental value. And so with such a standardized protocol, so we can skip the process of the meaning the computational setting that required advanced expertise of computational chemistry. And it's also noted, so as you can see from this scatter plots, and so there is always the discrepancy between the incomplete computer experiments and complex and uncertain real-world system. So one of the distinct feature of the our database is okay. So our database is used for the data resource or the machine learning, and machine learning is utilized to fill the discrepancy between the incomplete data from the computer experiment and the real world. So one such scenario is to exploit transfer learning. And so here I'd like to describe this one, okay? And so in a real world tasks, so okay, so our data is quite limited. And so, for example, the number of data typically available from the experiment is less than uh, 30 or 20. Okay, so by using such a small data, okay, so it would be difficult to acquire the highly generalized machine learning model. And so in order to overcome this limitation, so we perform the sim to real transfer learning using PolyOmics. Okay, so in procedure and fundamental foundation model is trained using the massive data from the computer experiments. And so this model is fine-tuned to a prediction task for in a real world physical property by using the limited data. So in this way, and we aims to obtain the highly generalized model. So with a high performance, and so which can be attainable by the scratch learning using only the experimental data. Yeah. So this is one typical scenario. Yeah. So here I'd like to describe the one illustrative example. And so, okay, so objective is to predict miscibility or solubility of the polymer and organic solvent. So this is a very important task in polymer research, such as polymer synthesis and plastic recycling and so on. Okay. So according to Florey-Hagen theory, and this is a classical theory of the polymer, theoretical polymer science, and so gives free energy of the mixing of the polymer P and solvent S is represented as follows. So details omitted here, but so, okay, first two term, combinatory entropy can be calculated once the polymer repeating unit with volume fractions are given. And so here, let's see the third term. So it's an important parameter which is called chi parameter. It appears in the third term. This is a very important parameter to describe the interaction of the polymer and the solvent. Yeah. So this is unknown parameter. So once such a parameter is given, so we can uh, generate a phase diagram, which is defined over the temperature T and composition phi. Okay, anyway, so the objective is to estimate computationally the chi parameter. Yeah, so to address this challenge, and so we performed integrated machine learning using the data from the simulation and experimentation. Okay. So experimental data for the chi parameter is quite limited. So it's consisting of the nearly 1,000 pair of the polymer and the solvent. Okay. So again, so using this data set only, so resulting machine learning predictive model is applicability domain is quite limited in a narrow region in the entire material spaces. And so in order to overcome this limitation, so we generated the data from the quantum chemistry calculation, so which is used for the computationally evaluate chi parameter for the nearly 10,000 polymer solvent pair. So these two data sets were combined to train the machine learning predictive model in order to overcome the barrier of the limited data from the real world application. So this is very important because the so in the real world data, so have some time and the critical bias in the data generation process. So such a bias come from the structure bias of the polymer and solvent. So number of polymer is and the number of solvent is very small, and so okay, so this is the polymer and solvent in experimental data set is distributed in a very narrow region of the huge material spaces in order to expand the applicability domain of the machine learning predictor. So it's important to generate data which are distributed in a broader region of the material spaces in this way. And another bias come from the selection bias of researcher. Okay, so this panel shows the histogram of the chi parameter in our experimental data set. So as you can, so each each pair of the polymer and the solvent is annotated by the soluble, insoluble by our annotator. Okay, so as you can see from this figure, so most of the data in our experimental data set come from the soluble pair of the polymer and the solvents. Okay, so this might be the selection bias of the researcher, which are interested in study of the polymer solvent miscibility. Okay. They prefer to observe the more on the data on the miscible pair of the polymer and solvent. Okay. So in order to reduce and bias, such a bias in experimental data, so now we use two different data from the such as the experimental chi parameter and the computational chi parameter from the quantum chemistry calculation. And so this is our model architecture. Okay, so polymer and solvent are input. And so its compositional and structural features are embedded into a latent space by using the neural network. And then hidden feature of the polymer and solvent. So their distance are calculated to obtain the Z. And this latent variable is further associated with experimental chi parameter and computational chi parameter with additional parameters such as temperature and composition. And by using the integrated data, so we train this model. Okay. So here is a result of the prediction, and horizontal and vertical axis indicate predicted and experimental chi parameter. Okay, so as you can see, and the predicted value exhibit good agreement to experimental chi parameter like this, and it's outperformed the performance of existing methods such as quantum chemistry calculation and empirical model based on the Hansen solubility parameter, which are widely used in this research field. Yeah. So here I'd like to describe the very important concept of the Sim2 real transfer learning, which is called scaling law. Okay. So, and as I described so far, okay, so by using the data from the PolyOmics, here the number of samples in the PolyOmics is denoted by small n. Yeah. So we first retrain the foundation model and which are fine-tuned to the predictive model for the experimental property by using a limited amount of experimental data. Yeah. In such a workflow, yeah, it's theoretically known the scaling law hold as described here. So that this means the generalization performance of the Sim2 real transferred model with respect to the prediction on the experimental property improved monotonically according to the parallel relationship as described here. Okay. So prediction error decrease with late alpha. Okay. and so monotonically, okay, with respect to the size of the simulation database, small n, and then n goes to infinity. So prediction error with respect to experimental property reach to achievable limit, which is called transfer gap. Yeah. So this is a theoretically explained. And then we can also measure the such a scaling behavior experimentally. Okay. So this is a result of the um, uh, scaling behavior for the prediction task of the experimental chi parameter. Okay. So as increasing the PolyOmics database from the 10 to 2 to 10 to 4, okay, so mean absolute error with respect to the experimental property prediction improved almost linearly. And so red line indicator predictive performance obtained from the scratch learning by experimental data used only, okay? And so as you can see from this figure, so very strong scaling has been observed successfully. So once such a scaling is observed, so we can estimate, for example, how many data are necessary to achieve uh, to uh, to the for the desired prediction accuracy in real world application. Okay? So this is a slide shows some example of the observed scaling behavior. So as you can see, the expansion of the polyomics from the 10 to 2 to 10 to 5. Okay, so there okay, strong scaling law observed across the various real-world tasks. For example, heat capacity and density and glass transition temperature and refractive index. Okay. So now, so I'd like to show them a more comprehensive experimental result. Okay, so now we use the 43 property dataset from the polyomics and this nearly 60 experimental property data set from the public database. Okay. So this metrics show the so presence or absence of the significant scaling. Okay. So among the nearly 250, 60 scenario of the sim-to-real transfer. Okay. So near, yeah, approximately in a 600 cases, so significant scaling was observed. And so this is a panel slide show there some several example. Okay, so the one of the important point to be remarked here is okay. So okay, so this okay, so this is a simple scaling behavior to the macro properties such as tensile stress at yield and the growth rate of crystal and also surface tension and so yeah. So you can observe the computational data, our computational data, polyomics database scale strongly even to the system for which and both and computation and experiments are difficult to automate, such as crystal growth rate and tensile yield stress, and direct evaluation based on the molecular dynamics simulation are very difficult, technically infeasible within short time period because of their large discrepancy in time scale of the simulation and the real world physical phenomena. Yeah. Such a scale gap can be the, can can be filled by using the sim to real machine learning and to bridge the gap between the computation and the real world system. Yeah. So this is a slide. This, okay. So far, and we have we have seen the scaling behavior uh, for the evaluated for the wide variety of the polymer together. But so here is the polymer is now classified into a specific type, such as the polystyrene and the uh, polyimide and so on. Okay, so scaling behavior for each polymer class is shown here. Okay, and so feature compared to the discrepancy of the simulation and experiment. Yeah. So MD calculated property and experimental uh, value for the glass transition temperature shown on the right panel. Okay. As you can see from the figure, even the simulation exhibit inconsistency to experimental data in this way. So resulting the sim-to-real transfer model exhibit scaling, significant scale like this. Yeah. So this means even if the experiment and the simulation results do not quantitatively match, but the generalization performance still scale. Yeah. This is one of the important uh, fact we need to consider. Yeah. And also, we can also measure the scaling behavior on the two-dimensional spaces on the number of sample from the experiment and computation. Yeah. So number of sample from the computer experiment and the real-world experiment is denoted by N and M. So according to a statistical machine learning theory, so it's known to follow this scaling power law relationship as described here. So this two-dimensional scaling can also be measured experimentally as increasing the N and M. So we evaluate the mean absolute error and so fitting the surface function to such an empirical observed scaling behavior. Yeah. So we can estimate such a function. And then taking the partial derivative with respect to the increase of the sample from the simulation and experiments, respectively, and then taking the ratio. Okay, so we can evaluate marginal rate of the substitution between the experiments and compute uh, the simulation can be evaluated like this, and then we can evaluate the number of computational data point equivalent to one experimental sample by taking the ratio. Okay. For example, in the case of the prediction task of polymer solvent miscibility, and so it was evaluated. One experimental measurement is almost equivalent to the 100 quantum chemistry calculation. So in this way, and we can evaluate the value of the data from the computer simulation and the real world system as well. Yeah. So this is another the example result to highlight a very important aspect of the sim-to-real transfer learning. Okay. So now let's see this one. Okay. So in this study, and we investigated how scaling behavior changed when the Gaussian noise with varying variance are introduced in the data on the pre-trained data set from the PolyOmics. Okay, so as the data source data is contaminated by the inclusion of the Gaussian noise. But so as you can see from this figure, as increasing the noise level in the PolyOmics, okay, so resulting strong scaling behavior of sim-to-real transfer model become the stronger and stronger. Okay, and then further increasing the noise level. And so generalization performance and scaling become the weaker. Yeah. So this indicator are very important. So things and how do we generate foundational data for the artificial intelligence application. So there is a trade-off between the quantity and quality of the data. But so this result indicate the so when if to construct the data platform for the AI training, okay, it would be a more efficient to generate large scale but so low to medium quality data. So this is a very important remarks to be considered when we construct the data platform for the AI application. Okay, so this is a short summary. Okay, so in the cutting edge field of science, okay, so it's difficult to acquire the sufficient amount of data applicable for the AI training. Even if we introduce the high throughput, the automated experimental system, okay. And so instead, so our strategy is to create the foundational data and the foundation model, okay. But so there is a discrepancy between these two domains, okay. So machine learning, especially in this context, so sim to real transfer learning is introduced to calibrate or fill the gap between these two domains. In this context, and foundational data, so here, should be designed to be transferable and scalable to a wide range of the downstream target tasks in the cutting-edge field of science. So this is our strategy for the data production for the AI for science. Yeah. Maybe so, yeah, time is over. And okay, so I'd like to skip this one. Okay. And so now, and we have successfully obtained the world's largest database from the computer experiments for the polymeric material. And so by combining the machine learning and the forward and the inverse design prediction workflow, okay, then maybe so we can go anywhere as long as a target system is computable or transferable by RadonPy computation workflow. And so remaining task is to extend the so what can be calculated to RadonPy and also the extend the database of the PolyOmics. So to accelerate this process, so we are now having organizing the very strong research team from the which consists of the more than 260 participants from the 3 national research institute, 8 university, and 37 private company. And so many experts of the computational chemistry from the industry academia has joined to our research project. And so they are now developing the wide variety of the automated simulation workflow for wide variety of the tasks in the polymer research. Okay. And also now we have a massive amount of the data from the computer experiment. And so next challenge is to bridge this computational database to real world. So to address this challenge, and so in this year, and we established a new team and PolyOmics team in RIKEN Trip Edges. And so in this lab, so we will implement the fully automated experimentation system for the polymer ultra high parallel, high speed combinatorial synthesis of the polymer and also the property measurement. And we are aiming to generate the world's largest integrated database from the automated computer experiments and automated real world experiments. And so these two data sets is utilized to generate a foundation model for the polymer research. And this pre-trained model is fine-tuned to a wide variety of the downstream application in the cutting edge of the polymer research. Yeah. Okay, so finally, I'd like to make a summary, deliver a summary. Yeah. So, okay, as already seen, okay, so in the cutting edge domain of the science, so it's difficult to acquire the enough amount of data. Okay. So going back to a history of the AI, and so, okay, so in order to innovate something by using the AI as a key driver, we need to generate massive data no one has gone before, yeah, no one has seen before. Yeah. Massive data is necessary. Okay. Middle to low scale data is not enough to to innovate, to make to realize the true innovation. Okay. So in order to achieve this challenge to go, and so so our strategy is to generate data in this domain. And so omics scale data production system is a very key component to address this challenge. And also such as co-creation is also the driving force to generate massive data. Okay. So in such a case, so there is a discrepancy between the data in the cutting edge and this foundation domain. And so machine learning model, especially the sim to real transfer learning, play a key role. And so then our foundation model is one of the distinctive feature of the foundation model is its capability of the integrating diverse data and also the transferability and scalability to a wide variety of the downstream tasks. Yeah. This concept is we are calling the polyomics. And so this is okay. So we are aiming to build a hierarchical data platform for generating AI and guiding by the more is better principle. Yeah. So this is the conclusion. Okay. Maybe so time has up. So so thank you for kind attention. Yeah. Thank you.